This topic is about how quadratic functions can be used to model and explore a range of practical contexts. Mathematical models use the tools of mathematics to represent real-life patterns and predict what is going to happen next. Feel free to pause as I go through the key concepts and some examples. So if you have an unknown quadratic equation, then it could be of one of the following forms. So it's in the first case, y is equal to a times x minus x1 times x minus x2 is when you know that x equals x1 and x is equal to x2 are roots of the quadratic. So when you know that the root, then there must be a scalar multiple of the product of the x minus x1 and x minus x2. In the second case, you know it's of that form when you know that PQ are the vertex. So remember the turning point, minimum point, and maximum point of that quadratic. And the general form ax squared plus bx plus c in all other cases. So this is the most complicated one when you don't have enough information about the roots or the vertex, then you have to use that form and possibly solve some simultaneous equations to get the answer. Okay, so we'll use these facts to help us answer some questions on modeling. Okay, so we have a question. A company makes a particular type of children's toy. The annual profit made by the company is modeled by the equation P is equal to 100 minus 6.25 times x minus 9 squared. Now, because it's a complete the squared format, I know straight away the vertex must be at 900. Okay, so that's a key thing that I can write down straight away, where P is the profit measured in thousands of pounds. Okay, be very careful. So P is measured in thousands of pounds. So whenever you get a value for P, times by 1,000 to find the profit in thousands of pounds. X is the selling price of any toy in pounds. Okay, so profit measured in thousands of pounds, selling price of toy is X. A sketch of P against X is shown in figure 1. Explain why A is not a sensible selling price for toy A. Explain why £15 is not a sensible price for the toy. Okay, because £15 is selling price, I will substitute x equals 15 into the profit, so P. So that means P must be equal to 100, take away 6.25, times 15, take away 9 squared, which is 100, take away 6.25 times 6 squared. Put that into the calculator. When you put that into the calculator, you get negative 125, which is less than 0. If the profit is less than 0, this is a loss, obviously. This represents a loss. So this is a loss, therefore not a sensible selling price for the company, definitely not, because the aim is to make a profit. Sensible, not a sensible selling price. Okay, B. Let's try B now. Given that the company made an annual profit of more than 80,000, so profit is more than 80,000. Again, because we know P is measured in thousands of pounds, that means P must be greater than 80. Find, according to the model, the least possible selling price for the toy. Okay, so that means we're trying to find profit is measured 100 minus 6.25 times x minus 9 squared, which must be greater than 80. Now, if I look back to my graph, my maximum point is 100. Somewhere here is 80. So we're trying to find the least possible selling price. So we're trying to find, if we find this point, then we know anything above that must be the least possible value, which will give us greater than 80. So if I change this inequality to an equal sign and solve it and find the least possible value, then anything above that must be the value that I'm looking for. So I'm trying to solve 100 take away 6.25 times x minus 9 squared, which is equal to 80. If I rearrange this, I get 6.25 times x minus 9 squared is equal to 20. 100 take away 80 is 20. If I divide by 6.25, I get x minus 9 squared must be equal to 3.2. And if I rearrange this now, I get x minus 9 is equal to plus or minus square root of 3.2, and x is equal to 9 plus or minus square root of 3.2. Now this gives me the two values. If I put this into my calculator, x is equal to 10.78 and 7.21. Okay, remember going back to our graph, we want the smallest one. So we need x is greater than 7.21, which means our minimum value must be x is equal to £7.22, because we need it greater than 7.21, greater than that value. So it must be £7.22. Okay, part C. State according to the model the maximum possible annual profit and the selling price of the toy that maximizes the annual profit. So the maximum point we've already worked out is up there. So C part 1, the maximum possible annual profit is P is equal to 100. That's where the maximum occurs, which means the profit is equal to £100,000. Okay, make sure you include the unit. Part 2, the selling price when it's maximum is x is equal to 9, which means the selling price is equal to £9 because it's just measured in pounds. So that would be my solution for part C. Okay, next question. A ball is thrown from the top of a cliff. The height h in meters of the ball above the ground level after t second is modeled by the function h of t is equal to 115 plus 12.25 minus 4.9 t squared. Give a physical interpretation of the meaning of the constant term 115 in the model. Okay, so 115 is just this part there. So what does that represent? Now we know at the start of the journey, so at the start of the ball's journey, when t is equal to 0, h of 0 is equal to 115. So before the ball has started moving, the height is equal to 115. So this must be the initial height of the ball, which implies that 115 meters is the height of the cliff, because that's where the ball is being thrown from, height of the cliff. Write h of t in the form a minus b times t minus c squared, where a, b, and c are constants to be found. Okay, so we've got h of t is equal to 115 plus 12.25 t minus 4.9 t squared. I like to rearrange it so I have my t squared term first, t term second, and constant at the end. So minus 4.9 t squared plus 12.25 t plus 115. The first thing I do is factorize the first two terms with the constant out. So minus 4.9, take it out so it makes life easier. So minus 4.9 times t squared. If you do 12.25 divide by negative 4.9, you get minus 2.5. So it's minus 2.5 t. Leave the 115 on its own because we don't want to overcomplicate it. Always leave the constant at the end. Okay, now complete the square. So I get minus 4.9 still remains here. T minus something squared, take away something, add the 115. So I need to half the 2.5, so I get 1.25. And then I take off 1.25 squared, which is minus 1.5625. Okay, now if I expand it, I need to clean it up, minus 4.9 times t minus 1.25 squared minus 4.9 times negative 1.5625 gives me positive 7.65625 plus 115. If I collect the last two terms together, I get negative 4.9 times t minus 1.25 squared plus 122.65625. So in this case, I'm just going to go here. My A is equal to negative 4.9. Oh, nope. Undo that is wrong. My A is the constant at the end, which is 122.65625. My B is 4.9 because the negative is already included here. And my C is 1C. My C is 1.25. Okay, so that's that done. I've completed the square there. C. Using your answer to part B or otherwise, find with justification I, the time taken after the ball is thrown for it to reach ground level. If the ball reaches ground level, it means h of t must be equal to 0. If h of t is equal to 0, it means minus 4.9, so I've just found out, t minus 1.25 squared plus 122.65625 must be equal to 0. Okay, now I rearrange, so I get negative 4.9 times t minus 1.25 squared must be equal to negative 122.65625. Okay, if I divide by negative 4.9 both sides, I get t minus 1.25 squared is equal to, I put that into my calculator, I get 25.03188 going on for quite a while. T minus 1.25, if I square root it, it must be plus or minus square root of 25.03188. Okay, and which gives me the value t minus 1.25 is equal to plus or minus 5.00318 using my calculator, which means t must be equal to 1.25 plus or minus 5.00318. Okay, if I do 1.25 take away 5.00318, it gives me a negative value. So t must be equal to, we want the positive one, 1.25 plus 5.00318, which gives me a value of t is equal to 6.2531877, blah, 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 which means t must be equal to 6.25. Okay, and the t is measured in seconds, so 6.25 seconds. So that's part one done. Part two. The maximum height of the ball above the ground and the time after which this maximum height is reached. So maximum height occurs at the vertex. So the vertex, if we look at it, so you got minus 4.9 t minus 1.25 squared plus 122.65625. So this occurs, vertex at 1.25, 122.65625. So the maximum height max is equal to 122.65625. If you look at it, what was it measured in meters? So meters at t equals 1.25 seconds. So that would be the full answer for that one. Okay, next question. Figure 1 is a graph showing the trajectory of a rugby ball. The height of the ball above the ground, h, has been plotted against the horizontal distance x meters measured from the point where the ball was kicked. The ball travels in a vertical plane. The ball reaches a maximum height of 12. So you know here, oops, it's 12. And hits the ground at point 40 meters from where it was kicked. So you know this is 40, 0. Okay, because it's symmetrical, because the quadratic is symmetrical, I know that halfway between 40 and 0 is 20. So that must be 20, 12. Okay. Find a quadratic equation linking h with x that models this solution. So you have two options. You can either use the two x-intercepts, the two roots, or you can use the vertex. I'm going to use the two roots to find the equation. So part A crosses x-axis at x equals 0 and x equal to 40, which implies y, normally we write y, but because y is labelled h must be equal to, again, because the quadratic is upside down, I know it's going to be a negative quadratic equation. So I'm going to write negative a. Remember, it's a scalar multiple of x times x minus 40. Okay, if you want to clean that up, that looks like h is equal to negative ax times x minus 40. Now we do know another point on the curve, which is 2012. So I need to substitute 2012 into h is equal to negative ax times x minus 40, which gives me 12 is equal to negative a times 20 take away 40. I get 12 on this side still. 20 take away 40 gives me negative 20. Negative 20 times 20 gives me negative 400. Times by negative a gives me 400a. If I do a is equal to 12 over 400, which turns out to be 0.03. So if I rewrite my equation, which implies, h is equal to negative 0.03x times x minus 40. Okay, so that's part A done. The ball passes over a horizontal bar of a set of rugby posts that is perpendicular to the path of the ball. The ball is 3 meters above the ground. Use the equation to find the greatest height of the bar from O. Now, because the bar is 3 meters above the ground, we know that h must be equal to 3. Okay, so we're trying to solve that. So that means if we have 3 here, somewhere here, we're trying to find the greatest one, so we're trying to find the higher one, yeah? So we're trying to find that one. Okay, if h is equal to 3, so that means if I rewrite, we've already got h. So negative 0.03x times x minus 40 must be equal to 3. If I times by 100 to get rid of this negative 0.03, so that just times by 100, then I get negative 3x times x minus 40 is equal to 300. If I expand the bracket, I get negative 3x squared plus 120x is equal to 300. If I move everything to the right hand side and divide by 3, so let's divide by 3 first, so I get negative x squared plus 40x is equal to 100. Okay, if I rearrange, I get x squared take away 40x plus 100 is equal to 0. Okay, x, using the quadratic formula, I get x is equal to minus b plus or minus b squared minus 4ac over 2a. which gives me 40 plus or minus negative 40 squared minus 4 times 1 times 100 all over 2 times 1. 40 plus or minus, get 1600, take away 1400, which is 1200 all over 2. Okay, 1200 can be written as root of 4 times root 300 all over 2. 40 over 2 gives me 20, so I get 20 plus or minus root 4 over 2 gives me 1, so plus or minus root 300. So that's what I end up getting. Okay, now because I want the maximum one, x must be equal to 20 plus the root 300. When I put that into my calculator, I get the value 37.32050808, blah, 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 which means if I round it, I get 37.3 to 3 significant figures. Next was measured in meters, so let's write meters. Okay, next question. It says give one limit of the model. Now, when we're obviously looking at modeling, one obviously is trying to represent real life, but there's some things that we can't take into account, or else it overcomplicates it. So one of them that we have not talked about is no wind or air resistance on the ball, because obviously it would not go smoothly in real life because it might be windy. Another thing is we're just assuming that the ground is horizontal, because in real life it's never horizontal. There's always parts where it's not. We're also assuming that the trajectory of the ball, so the path that the ball takes, is a perfect parabola, which in most cases, if you played football, you know, or rugby, you know that it doesn't travel like that. Also, another thing we're assuming is there's no obstacles in the path of the ball. So there are many limitations. You just have to choose one and write it down. So that's your final solution. Okay, the last question that I'll go through is a question about tunnels. So let's try to get here. So figure 2 shows the entrance to a road tunnel. The maximum height of the tunnel is measured as 5 meters. So maximum is 5, so somewhere here is 5. And the width of the base of the tunnel is measured in 6. So the whole thing is 6. So that means that must be 3 and that must be negative 3. Figure 3 shows the quadratic curve BCA used to model this entrance. Okay, I already labelled it on the modelled one. The points A, O, B and C are assumed to lie in the same vertical plane, and ground AOB is assumed to be horizontal. Find an equation for the curve BCA. So again, we've either got the vertex or the roots. So I'm going to take the root way. So because we have x equals 3 and x equals a negative 3 are roots, it implies y must be equal to, again, because it's a upside down U shape, it must be negative a times x minus 3 times x plus 3. Okay, so it must be of that form. I need to substitute the vertex, so substitute 0, 5 into y is equal to negative a times x minus 3 times x plus 3. So when I do that, I get 5 is equal to negative a times negative 3 times 3, which means 5 must be equal to 9a, which means a must be equal to 5/9. So therefore, my y must be equal to negative 5/9 times x minus 3 times x plus 3. And that would be it. Okay, so I've used my roots to find my general form and then substituted my vertex to find the exact form of my quadratic equation. A coach has height 4.1. So height 4.1, so B, height equals 4.1 and width equals 2.4. Okay, determine whether or not it's possible for the coach to enter the tunnel. Now, if it enters this tunnel, it must enter it via the center because it's symmetrical around the center. So if the width is 2.4, it must be 1.2 either way. If it's 1.2 either way, so it's rectangular, we need to see if it fits through this curve. So I need to find the corresponding y value. So at this point, what the y value is to find the height. So find height at x equals 1.2, which implies height is y, so y must be equal to negative 5/9 times x is 1.2, so 1.2 take away 3 times 1.2 plus 3. Now if you put that into your calculator, you get a value of 4.2. Y is equal to 4.2. So that means if the height at the width, when x is equal to 1.2, the height of the tunnel is 4.2. And because the height of the carriage is 4.1, as 4.1 is less than 4.2, it means it's possible for the coach to go through tunnel. Because the tunnel is 4.2 meters in height, the coach is 4.1 meters in height, therefore it must be able to go through. Okay, part C, I'll have to do part C here. It says, suggest a reason why this model may not be suitable to determine whether or not the coach can pass through the tunnel. Okay, we're assuming that the road is horizontal, so the road might not be horizontal, because if it's not horizontal, it might be higher in some places, which means it might not be able to go through. We're also assuming the coach needs to enter the tunnel through the center. And that means we're also assuming that the tunnel is single track, because that means nothing else can come through, one-way tunnel. We're also neglecting the fact there might be obstructions. So obstructions in the tunnel. Which may make it impossible to go through, for example, lights. So this model might not be suitable because all these things that we have to take into account in real life. Okay, any one of these reasons would be enough to get you the mark.